గుడ్ మార్నింగ్ మేడం.
ధర్మేంద్ర సార్,
చెప్పండి. పవన్ సార్.
మీరు అందరినీ అన్మ్యూట్ చేసేయండి ఫస్ట్.
ఓకే.
హలో, సార్ గుడ్ మార్నింగ్.
సో చెప్పండి పవన్ సార్. హలో
హలో
ప్రసన్న మేడం.
సార్ చెప్పండి.
సో మీకు నాకేమో కోహోస్ట్ ఇచ్చారు.
ఓకే.
సో నేను మీకు ఎలా రికార్డింగ్ ఇవ్వనా?
ఇవ్వండి సార్.
ఓకే.
హలో ధర్మేంద్ర సార్.
హలో,
యూట్యూబ్ లింక్ వచ్చింది చూడండి, అది అందరికి షేర్ చేయండి.
సో మీకు నాకేమో కోహోస్ట్ ఇచ్చారు.
ఓకే.
హలో,
సో నేను మీకు ఎలా రికార్డింగ్ ఇవ్వనా?
ఇవ్వండి సార్.
ఓకే.
ధర్మేందర్ సార్,
చెప్పండి సార్.
యూట్యూబ్ లింక్ వచ్చింది, మీరు కాపీ పేస్ట్ చేసుకోరు. ఆ లింక్ మీద కొడితే యూట్యూబ్ వస్తుంది చూడండి. మీరు మీరు ఏం చేయండి, రికార్డ్ స్టార్ట్ అయిపోయింది, మీరు ఏం చేయకండి, ఆటోమేటిక్ ఉంటుంది. మీరు కోర్స్ ఉంటారు, మిగతా వాళ్ళని కూడా కోర్స్ చేసుకోరు.
హలో, ఒకసారి ప్రసన్న మేడం నేను సార్ కోహోస్ట్ చేయాలి.
ఇంకొకరు ఎవరు?
ఇంకోటి అదే మనం చీఫ్ గెస్ట్ డాక్టర్ జె సూర్యనారాయణ గారు.
వచ్చాక ఒకసారి చూడండి. మీరు ఏం చేయాలి, స్టార్ట్ అయిపోయింది, మీరు ఏం చేయకండి, ఆటోమేటిక్ ఉంటుంది. మీరు కోర్స్ ఉంటారు, మిగతా వాళ్ళని కూడా కోర్స్ చేస్తారు.
హలో, ఒకసారి ప్రసన్న మేడం నేను సార్ కోహోస్ట్ చేయాలి.
ఇంకొకరు ఎవరు?
ఇంకోటి అదే మనం చీఫ్ గెస్ట్ డాక్టర్
చూడండి. మీరు ఏం చేయాలి, స్టార్ట్ అయిపోయింది,
హలో.
హలో, ఇంకో మేడం ఏది, ఆమె లేనట్టుంది. ప్రసన్న మేడం
ఉన్నారుగా? ప్రసన్న మేడం ఉన్నారు.
ఏది ఏది ఇక్కడ కనబడట్లేదు.
మళ్ళీ లాగౌట్ అయ్యారు.
లాగౌట్ కాకండి సార్, ప్రాబ్లం అవుతుంది. వచ్చినట్టుంది సార్. యూట్యూబ్ చూస్తురా?
చూసాం.
లింక్ వాట్సాప్ గ్రూప్ లో పెట్టండి, మీ గ్రూప్ లో.
పెట్టాం. ఉన్నారుగా? ప్రసన్న మేడం ఉన్నారు.
వచ్చాను సార్, జాయిన్ అయ్యాను.
Good morning. morning, Dharmendra.
Sir, good morning, sir.
Morning.
Hello, good morning. Good morning to everyone.
Morning, morning.
Good morning, sir.
Morning.
Good morning, sir.
Good morning. I will just share my presentation. Just 1 minute. Be able to see my presentation?
Yes, sir.
Okay, fine.
Okay.
So, Sridhar sir, can we start the program? Webinar? Sridhar sir?
Hello. Hello.
Sir,
Hello.
Sridhar sir?
Am I audible?
Yeah, yes sir.
Yeah.
Suryangar, good morning.
Good morning, sir.
Morning.
How are you?
Fine, fine, thank you.
Can we start the program, sir?
Yeah, we can start.
Yes, yes, we will
Okay.
start.
Okay. So before we start, I request all the participants to mute your audio and video. And your questions, you need to post it in the chat box only. And at the end of the sessions, you will get a feedback form. And if you fill the feedback form only, e-certificates will be given. So with that, I am starting the session. Good morning to one and all. I, Dr. K.V. Dharmendra Kumar, Associate Professor of Physics, on behalf of Department of Physics, VBIT, welcome you all for today's webinar on magnetic field effects on titanium dioxide-based dye-sensitized solar cells by Dr. J. Suryanarayan Garu, Associate Professor of Physics, IIT Hyderabad. Now, I request our beloved Vice Principal and HOD H&S, Dr. Sridhar Garu, to speak a few words on this webinar. Sridhar, sir.
Thank you, Dr. Dharmendra. Good morning, one and all. Today's guest speaker, Dr. J. Suryanarayan Garu from IIT Hyderabad, professors from VBIT and different colleges in and around Hyderabad, my dear faculty members and participants. A very good morning to one and all. At the outset, I welcome you all to this webinar on titanium dioxide based solar cells. I think all of you might be going through the literature. A lot of research is going on with the titanium dioxide. It has got a lot of advantages. First is it is non-toxic. Second and most important, it is highly chemically stable. And third one is it is very cheap. Maybe because of these three reasons, lot of work is going on using this material. If you see, titanium dioxide is used in solar cells. They are using it in batteries. They are using it in sensors, polarizers, so and also in photocatalysis. And it is also observed that titanium dioxide has got high refractive index. So it can be used as coatings and using its optical properties. And the stress, the mechanical stress of titanium dioxide is convenient to use it in microelectromechanical systems, MEMS. Recently, we have also observed in one of our works, we used titanium dioxide as a dopant in manganese zinc ferrites, and because of this doping, there is an improvement in the antimicrobial properties also. So you take any field nowadays, we can use this titanium dioxide. So I hope thus that today's lecture will be of immense importance to all the participants, especially to those who are doing their research work. I once again thank Dr. J. Suryanarayana for accepting our invitation. Thank you, sir.
Okay. So thank you very much for your nice introduction, Professor Sridhar, and then Professor Dharmendra. Okay. So today I'm going to speak on magnetic field effects on titanium dioxide based dye-sensitized solar cells. So as Professor Sridhar mentioned, like this titanium dioxide has been used at many places, but whatever work that I'm going to present is something different which has not been attempted by anyone else. So basically, like we wanted to improve the efficiency of titanium dioxide based solar cells using the magnetic fields. Like we wanted to control the charge transport in the titanium dioxide based solar cells using a magnetic field, using some important magnetic phenomena like spin orbit coupling, then Lorentz force effect, and the demagnetization fields. This is the first attempt that we have made to improve the solar cells in this kind of devices. Okay, these are, I'll just brief about our laboratory. Like our laboratory is basically magnetic materials and device physics laboratory. The motivation of this lab is to develop the smart materials and study their fundamental properties and foresee their applicability in various devices. Okay, these are some of my students who have been working very hardly to get very good results. And then like our research topics are like we work on rare earth intermetallics and magnetic thin films, magnetostrictive sensors, non-volatile memory devices, magnetic field effects on solar cells, magnetic nanoparticles for biomedical applications, biosensors, ultrasonic transducers. So basically, I can classify our laboratory work as metal spintronics, magnetic materials for energy and devices, the mesoscopic physics. Okay, so the molecular spintronics, and then biosensors, cantilever based beam based biosensors. Basically, like when we put biomolecules on top of this cantilever, the resonant frequency of the cantilever changes, and hence one can find what kind of molecule that exists on the cantilever. So then we also work on RAM devices, resist to random access memory devices. I think during the last talk that I have given at VB80, I have given a presentation on this RAM devices, the resist to random access memory. And we work bio RAMs, like detection of biomolecules using RAM devices, then mechanically controlled break junction devices to study the quantum mechanical properties like conductance quantization and quantum mechanical tunneling phenomena using ferromagnetic nanostructures. Okay, so these are some of the topics that we have been doing in our laboratory. So in today's talk, I specifically I would like to focus on magnetic field effects on solar cells. Okay, the plan of the talk is something like I will just brief you some of the solar cells that we have, and then the various types of solar cells like first generation solar cells, second generation solar cells, third generation solar cells. And I would also brief you why third generation solar cells are more important in comparison with the first generation solar cells. Then I would like to go with my topic, the magnetic field effects on solar cells. As I just mentioned, like we would like to utilize the important phenomena, something like the spin orbit coupling, Lorentz force effect, and demagnetization fields. Okay, so the spin orbit coupling is basically like suppose if we take any atom. In atom, electrons will revolve around the nucleus. As a result of this fact, the electron would attain orbital motion. Okay, this orbital motion will give a magnetic moment, which we can call as orbital angular momentum. And apart from that, like electron will also persist, the electron spin will also persist around its own axis. This gives us the spin angular momentum. Okay, the total angular momentum is basically J is equal to L plus S, the orbital angular momentum plus the spin angular momentum. Okay, so we would like to use the interaction between the orbital magnetic field and the spin magnetic field, and improve the solar cell efficiency. This is one of our aim, to improve the solar cell efficiency using the spin orbit coupling. Whereas the Lorentz force effect, the Lorentz force is basically like when you have a charged particle which is moving, when you apply the electric and magnetic fields perpendicular to the charge motion, the electron would attain spiral motion. Okay, this effect is called the Lorentz force effect. So we would like to use this effect also in our device to improve the solar cell efficiency. Then demagnetization fields. Demagnetization fields means, like as you see, like whenever you take magnetic nanoparticles, there will be stray fields around the magnetic nanoparticles. We would like to utilize these stray magnetic fields to improve the solar cell efficiency. These are the three important phenomena that we would like to use to improve the solar cell efficiency of the titanium dioxide. And this work has been published in many news journals, newspapers, like a lot of media attention was happened on the work that we have carried out. Okay, first of all, what is meant by a solar cell? The solar cell, let me start from the beginning. Like I presume that there are many people who do not know fundamentals about the solar cells. That's why I would like to start from the scratch and then build slowly so that you can understand everything, whatever that I say. First of all, what is meant by a solar cell? A solar cell is the one which converts the sunlight into electricity. Okay, so for instance, if you put a solar panel on top of house, the sunlight will fall on the solar cell, and then you would get the direct current, and then using the inverter you can convert it to alternating current. This alternating current you can use for the household purpose to lit the lamps in the house. Okay, so the primary photovoltaic markets, so they depend on the household solar cells and commercial rooftops and ground mounted solar cells. There are various ways by which we can use these solar cells to convert the sunlight to the electricity. So whatever sunlight, like for instance, if you consider the amount of sunlight that we receive from the sun to the earth, in an hour, whatever sunlight that we receive from the sun to the earth in an hour is enough to meet the world's energy demand for a whole year. That means whatever light that we receive in 1 hour from sun to the earth, that is sufficient to meet the energy demand for a whole year for the entire world. That means we are not able to utilize the power that we are getting from the sunlight. Very little fraction of sunlight we are able to use. Annually, we receive the 4 into 10 power 18 joules of an energy from the sun. We consume energy of 3 into 10 power 14 joules. So the lot of energy is being wasted. We don't have resources. We don't have any other devices to utilize that kind of energy that we receive from the sun. Okay. So there are various ways by which we can generate the electricity. One by solar cells, another one by wind energy, another one by thermal energy. Okay, by thermal. Okay. So this is the spectrum, the irradiation of the sun. Like this is the wavelength versus photon flux that we receive from the sun. Like it varies, the wavelength varies. Like it's not like we don't receive the sunlight at one particular wavelength, we receive in a broad spectrum. We receive in a broad spectrum, and as a result of this fact, only one material cannot give. Yeah. Any question? Okay, fine. So this is the kind of the spectrum that we receive from the sun. For instance, if you consider a solar cell, it works based upon the photovoltaic effect. So what is meant by photovoltaic effect? So a photovoltaic effect is basically the conversion of incident solar radiation into electricity is called as the photovoltaic effect. Okay. So now in a solar cell, we will have a PN junction. Like if you take a P-type semiconductor and N-type semiconductor, if you bring them together, like you will have the PN junction. So whenever you bring the PN junction, like whenever you form a junction, there will be built-in potential. So this built-in potential or the electric field will be generated. This we can call as a depletion region. As a result of this fact, the electrons cannot move from this side to this side, or holes cannot move from this side to this side because of this depletion region. Okay. So now, like this is basically the schematic of PN junction solar cell under no light when we don't impinge any light. This is the scenario. When you impinge the light, what would happen is there will be flow of electrons from the P-type to N-type and N-type to P-type. Okay. So this device you can characterize in various ways, like in the short circuit condition and in the open circuit condition. Okay, this is the typical IV characteristics that we can obtain from any solar cell. So the current generated in the solar cell depends upon the area of the device that is exposed to the solar cell. And then like this is the IV characteristics that one can imagine. Like as you can see, like here, this is the current density equation. J net current before we apply the light. J net is equal to Js exponential QV by nkt minus 1. And when you impinge the light, the current characteristics will change. J is equal to Js into exponential QV by nkt minus 1 minus J phonons. Okay. So this much amount of current will be generated as soon as you expose the light. VOC, this is the open circuit voltage when the current density is 0. JSC is the short circuit current density when the open circuit voltage is 0. And the J maximum, this is the maximum amount of current density that we can obtain from any solar cell. And VM, it is the maximum voltage that we can obtain from the solar cell. And then MPP, the maximum peak point. This is the maximum peak point. Okay, so based on these parameters, we can define important solar cell parameters like the fill factor and then the efficiency of the solar cell. Okay, the fill factor is defined as Vm, the maximum voltage multiplied with the maximum current density divided by the open circuit voltage multiplied with the current density, short circuit current density. This actually gives the fill factor. So this signifies how square your IV characteristics are. Okay. So whereas the efficiency you can define as Vm multiplied with Jm divided by Pn. So this is how one can define the fill factor and the efficiency. So the power conversion efficiency of a solar cell is determined by the three important parameters like short circuit current density, open circuit voltage, and the fill factor. Okay. So the fill factor characterizes how square the JV curve is, as I just mentioned, and also it also represents how difficult or how easy the photo generated carriers can be generated out of photovoltaic device. So this fill factor is very, very important parameter to characterize any solar cell device. Okay, ideally the fill factor must be 1 when JV curve is a rectangle. Like for instance, if you have a JV curve like a rectangular JV curves, you can actually get the fill factor 1. That means the maximum amount of power you can convert as current. Maximum amount of sunlight you can convert as convert as current. Okay. So generation of the electron hole pairs, basically like when you impinge the solar light, sunlight on top of the PN junction, the electron hole pair will be generated, and this will give us the current. This will give us the current, and that current we will store in the batteries. Okay. So now the question is why we have to use different materials for conversion of the sunlight into the electricity. Okay. The reason is that, as I mentioned, like whatever light that we receive from the sun, it will not come at one energy. It will not come at one energy. You will have a broad spectrum. So different materials will respond at different energies. Like for instance, depending upon the band gap of the material, some materials would respond at one energy, some materials would respond at another energy. So that's why we have to use different materials to convert the sunlight to the electricity. Like for instance, if you consider a silicon, it is having band gap around 1.1 or so, whereas for the gallium arsenide, it is having around 1.4. CuGa selenium 2, it has the band gap around 1.6. Okay, so the absorption capacity of different materials will be different. As a result of this fact, different semiconducting materials we can use for the solar cell applications. So now the question is, what kind of solar cells we have? What kind of solar cells we have? We have the first generation solar cells. These solar cells are silicon based solar cells. Like the silicon based solar cells are single crystals based one or the polycrystal materials. So for the people who do not know about a single crystal is basically the one in which all the grains will be oriented in one direction, whereas in polycrystal the grains will be oriented, like many grains will have different orientations. Like in a single crystal, if I say silicon 111, that means all the grains will be oriented in 111 direction. Whereas in a polycrystalline material, you can find different grains like 111 grain, 100 grain, 110 grain, and so on. Many grains would exist in a polycrystalline materials. So whatever solar cells that we are seeing in today's market, they are based upon the silicon based single crystal solar cells, and sometimes people also use the polycrystalline based silicon solar cells. So now we also have the second generation solar cells. They are basically thin film made up of thin films, and the copper, indium, gallium selenide, gallium arsenide, cadmium selenide, or cadmium telluride based solar cells. These are basically the second generation solar cells. So what are the advantages of the second generation solar cells? The advantages are they can absorb the incident light within thin layers, and the limitations are environmental toxicity and complex fabrication methods. We will have a complex fabrication method to develop this kind of solar cells. Like you have to develop these solar cells in the clean room, and then using the e-beam lithography and then sputtering techniques you have to develop. Okay. So whatever may be the case, we have like right now, whatever solar cells that we are using, they are basically based upon the silicon one. So how to generate a silicon photovoltaic material? Like initially we'll take a silicon feedstock, then we'll develop the ingot, then we'll slice this ingot, and then cell fabrication. Once we slice, we'll get the cell and the module encapsulation and photovoltaic system, which will be there on top of the house. This is the process steps that will be involved to develop the silicon based photovoltaic cell. Okay. So if you consider the multi-junction solar cells, they actually gives the higher efficiency. It is because of the fact that, as I mentioned, like different materials will have different band gaps, and correspondingly the absorption of the sunlight will be different at different energies. Like for instance, if I consider the gallium indium phosphide, it is having the band gap around 1.8 electron volts. So this absorbs the energy from this energy region, whereas the gallium arsenide will absorb the energy from this region, from the green region. The germanium will absorb the energy from this region. Okay. And then different materials will absorb like different energies from the spectrum that we receive from the sun. Okay, so this is basically the conventional multi-junction solar cells, and this is a new solar junction multi-junction solar cell. Okay, and we also have thin film solar cells. One can deposit low cost methods and less materials are used. Like if you consider the cadmium selenide or cadmium telluride material, will have the n-type. The cadmium selenide will be n-type material, and cadmium telluride will be p-type material. And at the bottom, you will have transparent conduction oxide, conducting oxide, and all these things will be deposited on top of glass substrate, and at the top you will have a metal electrode to close the circuit. Okay, so the kind of efficiencies that people have obtained using this cadmium selenide or cadmium telluride based solar cells is of the order of 17.3 electron volts. And then the challenge is to have the cadmium selenide layers without having pinholes. Like these cadmium selenide layers are prone to have pinholes. Like the entire solar cell efficiency will depend upon how smooth or high continuous your film is. For instance, if I have the pinholes in the film, you cannot get the best efficiency from the solar cell. And on top of that, these materials are also toxic. Like hence, we have to have different alternatives to convert the sunlight into the electricity. So this is the world's most efficient solar cell ever produced, like 43.5% at 418 to 655 suns. Okay, this is the maximum efficiency that people have achieved until now. This is on triple junction solar cells. So we also have copper, indium, gallium based selenides. The world's record efficiency of the order of 20.4% has been achieved in the solar cell based upon this one, like cadmium, indium, gallium selenide based solar cells. And it is also very difficult to handle many thin films. It is due to the fact that whenever you have multi-junction solar cells, you have to see the interface physics, like how the interface is formed, whether the interface is uniform or not, how smooth the interface is, how rough the interface is, whether there exists a bonding between the interfaces or not. All these factors will come into picture, and it would influence the efficiency of the solar cell. Okay, so that is all about the second generation solar cells. Like in the first generation solar cell, we have solar cells based upon the silicon, and in the second generation solar cells, we have solar cells based upon the multi-junctions, the cadmium selenide or cadmium telluride, and also like we have the gallium arsenide based solar cells. Now, if you consider the third generation solar cells, we have dye sensitized solar cells, and then organic solar cells, quantum dot solar cells, and perovskite solar cells. These are all the third generation solar cells. So the third generation solar cells, like we use basically the materials which have the wide band gap metal oxide semiconductors, like titanium dioxide, the zinc oxide, and tin oxide. And these dye sensitive solar cells, they are having advantages in comparison with other solar cells because of the fact that they are very simple, economic, environmental friendly, and renewable alternatives to silicon based photovoltaic solar cells. Now the limitations are the efficiencies are very low compared with the perovskite solar cells, but still there is a lot of scope to improve the efficiency of these dye sensitive solar cells. The reason why so much of research is going on dye sensitive solar cells is basically they are very cheap. They are very cheap and very simple, and then with which one can also get the best efficiencies from the solar cells, like if much research goes on. Okay, the advantages are simple structure and device fabrication is very easy. In a short while, I will tell you how to develop a dye sensitized solar cells. But as of now, this is the basic scenario. Like in the third generation based photovoltaic solar cells, we have dye sensitized solar cells, organic solar cells, quantum dot solar cells, and perovskite solar cells. Okay, until now I have classified 3 generations of solar cells: first generation solar cells, second generation solar cells, and third generation solar cells. In first generation solar cells, we have silicon based solar cells. And in the second generation solar cells, we have multi-junction solar cells. And in the third generation solar cells, we have organic solar cells,
feedback
solar cells, perovskite based solar cells. Okay, this is a chart. This is a chart between the year and the efficiency, like people have obtained. Like for instance, if I consider the dye sensitive solar cells, it actually gives the efficiencies of the order of 10%. Whereas if you see the three junction solar cells, the efficiencies have gone up to 45%. Have gone up to 45%, and you can actually see this chart for different solar cells. How much of efficiencies they give, and this also actually give how the efficiencies of different solar cells have evolved with years. Like for instance, if I consider the three junction solar cells, it started with 15% efficiencies. Now with the research, people could able to obtain efficiencies up to 45%. So in the same way, the efficiencies of dye sensitive solar cells can also be improved further by doing a lot of research on this area. Now we have seen different solar cells and their efficiencies as well. Now the factors that would affect the efficiencies, what are the different factors that would affect the efficiencies? Like for instance, if I consider the light that we receive from the sun, the sunlight consists of spectrum of the wavelengths. Like as I mentioned, like it cannot come at one wavelength, it will have the spectrum of the wavelength. So the semiconductor material cannot respond to the full spectrum. So if a semiconductor material which will have a fixed band gap cannot respond to the full spectrum. So that is the reason why the solar cells which have the multi-junctions could able to produce higher efficiencies. It is because like three different materials would have three different band gaps. As a result, it can absorb light from the different spectrum or from the different wavelengths, so that the efficiency of the solar cell would enhance. And as much 30% of the light is reflected from the surface of the cell. Like most of the light that we receive from the sun, we are not able to use. On top of that, the impurities can also cause the charge to recombine and therefore not generate electricity. Okay, so the impurities, like you must make sure that the impurity percentage is very low in our device. So these are the two important factors that would influence the efficiencies. The first one is semiconducting materials cannot respond to the full spectrum. And the electron hole pairs will also recombine very easily because of the impurities. So now our main aim is to make sure that the most of the sunlight absorbs by the solar cell. And second thing is we must be able to enhance the recombination time. That means the electron holes should not recombine very easily. Like there must be lot of time to recombine. There must be a gap between the generation of the electron hole pairs and the recombination. We must make sure that the recombination time must be enhanced. So the other factors, these are the other factors that would affect the efficiencies, like the angle of incidence of the sunlight and the cloud cover, shading, dirt, snow, or other impurities on the cell surface. The efficiencies goes down as the cell gets hotter. These are the other important factors that would affect the efficiencies of the solar cells. So let's try to discuss more about the dye sensitized solar cells. Like dye sensitized solar cell, it's basically very simple structure, and then the device fabrication is very easy. One can develop dye sensitized solar cells very easily, and they are environmental friendly, and they are also economic. Like with less material and with less money, we can develop these dye sensitized solar cells. Okay. So the composition of the dye sensitized solar cells are basically the semiconducting electrode. Like it will have a semiconducting electrode, dye sensitizer, redox mediator, and then the counter electrode. In a short while, I will try to discuss like how a dye sensitized solar cell would work. This is a kind of the schematic that one can imagine as far as the dye sensitized solar cell is concerned. Like we have a glass substrate and the bottom electrode, active material, titanium dioxide or semiconducting material, a dye dye which responds to the sunlight, and an electrolyte, then a platinum material, and FTO, and a glass substrate. Okay, so the first report of dye sensitized solar cell device with an efficiency of 2% has been reported by the group of Gratzel in 1991. Okay, so he is the first person who invented this dye sensitized solar cell. That's why these dye sensitized solar cells we can also call as Gratzel solar cells, Gratzel solar cell. Just 1 minute. The Gratzel solar cells. So one can also improve its efficiencies, like although the efficiencies of 2%, those have been reported, people also could able to improve the efficiencies of the solar cells by changing the photosensitizer like dye, and then counter electrodes, the kind of electrodes that we use, and electrolyte, like here we use I minus, I3 minus. One can also replace this counter electrolyte by other electrolytes. Okay, so by improving the above, by changing the photosensitizer, by changing the counter electrode, by changing the electrode, people could able to get power conversion efficiencies of the order of 11.9%, 11.9%, from 2% to 11.9%. It's a huge, like still lot of research is going on in this dye sensitized solar cells. So how a DSSC operates? So the question is how a dye sensitized solar cell operation takes place. So initially the light absorption electron hole pair generation happens, like as soon as the light falls on the solar cell, which consists of dye, active material, and electrolyte, the electron hole pairs will be generated. Okay, for instance, if I consider the dye N719 dye, like it will have the ground state, the excited state. In the excited state you will have the singlet state and the triplet state. Okay, so the photo generated electron hole pair or exciton, we can also call the pair of electron hole as exciton. Okay, so this exciton exists in the singlet or triplet states. Like once the light falls on the solar cell, the electrons which exist in the ground state, they can go to the excited state. So these excitons can be in the excited state, it can be in the singlet state or the triplet state. The electrons are then transferred from either of these states to the conduction band of titanium dioxide. The importance of this dye is basically first it will absorb the electron, first it will absorb the sunlight from the sun, and then it will excite the exciton in the ground state to the excited state, and from there it will transfer the exciton to the conduction band of the titanium dioxide. And the oxidized dye is then regenerated by electron capture from the redox electrolyte. Okay, so like as I mentioned, like the oxidized dye, since the electrons are going from dye to the conduction band of titanium dioxide, so these electrons must fill. So these electrons will come from the electrolyte to the dye. Okay, so the electron is returned to the cell via an electrolytic reduction reaction at the counter electrode. Like whatever electrons that goes, it will be, since this is in the closed circuit, again electrons will come to the electrolyte. This is the process of or operation of a dye sensitized solar cells. Initially the sunlight will fall on the solar cell and dye will respond to the sunlight, and whatever electrons or hole electrons that exist in the ground state, they will go to the excited state. The electron pair will go to the excited state. They can be in the triplet state or the singlet state. Okay, from the triplet state to the singlet state, this exciton will go to the conduction band of titanium dioxide. So as a result of the reduction of this reduction of this dye, so the electrons will come from the electrolyte to the dye, and then since this is in the closed circuit, again these electrons, whatever electrons lost by this electrolyte, will come to this electrolyte. This is a closed operation of a dye sensitized solar cell. So in the structural details, like the kind of dye that we have used in our sample, in our device, is basically N719 dye, and it has a broad range of absorption spectrum from 800 to 2500 nanometers. As I mentioned, like a semiconducting material, it will have very narrow absorption spectrum, like it cannot absorb the entire light that we receive from the sunlight. Instead of that, if you use a dye, it can absorb the sunlight, the maximum range of the light that we receive from the sunlight. Like for instance, if we see N719 dye, it absorbs the light in the range of infrared, like 800 to 2500, to the visible region 382 to 700 nanometers. Okay, and these are also having the, like this dye is also having the longer excited state lifetimes. Okay, the excellent thermal and electrochemical stability, like it cannot react much easily with other materials, and then favorable alignment of ground and excited energy levels. Okay, these are the some of the important characteristics of N719 dye. If you consider the titanium dioxide, it is a wide band gap semiconductor, like it has 3.2 electron volts, and then high refractive index, like 2.4 to 2.5, and then it can form in the rutile, brookite, or anatized phase. Like in this work, we have used the anatized titanium dioxide to develop the solar cells. Okay, these are some of the important structural characteristics of the device. This may not be important, but however, you can find the structural details of anatized TiO2 in literature. I don't want to go deep into the details of the structure of the titanium dioxide. The more importantly, we have used the anatized TiO2. Okay, so here I must tell one important physical concept which can be called as the intersystem crossing. What is meant by intersystem crossing? Like as I mentioned, like we have chosen a dye of N719, and here over here we have a singlet, we have a ground state S0, and we also have the excited state. S0 represents the ground state, S1 represents excited singlet state, and T1 represents the excited triplet state. Okay, please remember this terminology. S0 is the ground state, S1 is the excited singlet state, T1 is the excited triplet state. For instance, an electron in a singlet ground state S0 of dye molecule can be photoexcited to either S1 or T1 excitonic state. Okay, whatever electron that exists in the S0 can go from the ground state to the excited state. It can go to the excited singlet state, or it can also go to the excited triplet state. So now in the presence of strong spin orbit coupling, like what can happen is, like the electron can go to the ground state to the excited state, or the electron can also come from the excited state to the ground state, excited singlet state to the ground state, and however it cannot come from the triplet state to the ground state because of the spin selection rules. The selection rules will not allow electrons transitions from the singlet singlet excited state to the triplet excited state. Okay, let me repeat. Electron can go from the ground state to the excited state, and it can also come from excited singlet state to the ground state. However, the transition between the singlet excited state to triplet excited state cannot happen because of the spin selection rules. So now the question is, how can we unlock this transition from the singlet excited state to triplet excited state? Okay, it has been proved that in the presence of a strong spin orbit coupling, like if you take an element which is having the strong spin orbit coupling, an excitonic transition from the short-lived singlet excitonic state to long-lived triplet excitonic state occurs. If I have an element which is having a strong spin orbit coupling, that will allow the electronic transitions between the singlet excited state to the triplet excited state. Okay, so this phenomenon is called as the spin rephasing or the intersystem crossing. Okay, the transition between the singlet excited state to the triplet excited state is called as the intersystem crossing. Okay, So as the photogenerated excitons have higher lifetimes in the triplet excitonic state. So in comparison with the singlet excitonic state, the triplet excitonic states will have long lifetime. Like for instance, if an electron goes to the singlet excited state, it will spend very less time and it will go to the conduction band of the semiconducting material. But however, like if an electron goes to singlet excitonic state, and further if it goes to the triplet excitonic state, and it can spend more time in the triplet excitonic state and then goes to the conduction band. Now the question is, what is the advantage of spending more time in the triplet excitonic state? The advantage is that one can improve or one can enhance the recombination. One can enhance the recombination time. Okay, so if electrons goes to the triplet excitonic state, it will spend more time without recombining. As a result of this fact, the efficiencies of the device can be enhanced. So all these things will happen if you have a strong spin orbit coupling element. A strong spin orbit coupling element. This spin orbit coupling will unlock the transition between the singlet excitonic state to the triplet excitonic state. Okay. So for this reason, we have used the holmium oxide. The holmium oxide we have used for our purpose. Like the holmium oxide has been widely prepared, widely regarded as material with excellent optical properties. Like it can absorb more light, and then it is also having a strong paramagnetic. It is also a very strong paramagnetic, and it also consists of a strong spin orbit coupling, very strong spin orbit coupling. So our main motivation of this work is to unlock the transition between the singlet excited state to the triplet excited state, so that the electrons will spend more time within the device before they recombine. As a result of this fact, the efficiencies of the solar cell would enhance. That's the reason why we have chosen the holmium oxide for our purpose. The holmium oxide is having a very strong spin orbit coupling. This strong spin orbit coupling will unlock this transition, which leads to the enhancement in the efficiencies of the solar cells. And these are some of the structural aspects of the holmium oxide, and which you can read from the literature. Even from Wikipedia, you can read through the structural aspects of holmium oxide. The most importantly, it has the strong spin orbit coupling. Okay, so we have used three different materials, three different elements, like N719 dye, like we have discussed about N719 dye, and then we also discussed about the titanium dioxide, and then holmium oxide. What is the importance of using the holmium oxide in our device? So now, how to fabricate a dye-sensitized solar cells? How to fabricate dye-sensitized solar cells? In our work, we have developed two different devices, like titanium dioxide plus holmium oxide, which we call as HTO. HTO means holmium titanium dioxide based device, and Fe, titanium dioxide plus Fe3O4, FeTO, HTO and FeTO. Okay, so before we developed three different devices. One is the parent device, the titanium dioxide device, HTO device, FeTO device. So initially, you apply titanium dioxide paste on a clean FTO glass slides, then center at 475 degrees centigrade for 30 minutes. And parallelly, you can also prepare N719 dye in methanol. And titanium dioxide anodes are stained in dye solution for 12 hours. After centering, keep your titanium dioxide anodes in dye for 12 hours. Then the sintered platinum counter electrodes at the rate of 450 degrees for 10 minutes. Like you have to heat at 450 degrees for 10 minutes. And then, like once if you are done with all these things, attach electrodes together with the binder clips, and 2 drops of electrolyte is added to the device. Okay, so this is very simple fabrication procedure. It is also very much economic. As a result, so many people are doing research on this dye-sensitized solar cells. Without much cost, you can develop these dye-sensitized solar cells. Okay, so now let me go to my results, like effect of the external magnetic field on the transport properties of HTO dye-sensitized solar cells. or using the spin orbit coupling, in our device to enhance the charge transport within our device. Okay. So this is the schematic of the device that we have developed, like FTO, the bottom electrode, FTO, platinum bottom electrode, and then active material, titanium dioxide, and then dye, electrolyte, and the top electrode, FTO, and then the sunlight will fall, sunlight or a solar simulator. We have used a solar simulator to characterize such device. Okay. So the HO, TO, N71 and I, like this, the top electrode and the bottom electrode, we have connected using Keithley 2400, which actually work like a source meter and the sensing meter. Like we can send the current and measure the voltage, or send the voltage and measure the current. Okay, by impinging the solar light of AM 1.5 spectrum. This is the cross-sectional view of the DSSC device. So before we make this device, we also characterized our materials with various characterization tools like X-ray diffraction. X-ray diffraction, it actually gives the structural parameters and identification of the phase of the material. Like so, this X-ray diffraction will give the X-ray diffraction peaks only if one condition is satisfied, that is the Bragg's condition, which is basically 2d sin theta is equal to n lambda. So whenever the incident light's wavelength, incident X-rays wavelength matches with the interplanar spacing, the Bragg's condition will be satisfied, and it actually gives the diffraction pattern. Okay, from this diffraction pattern, you can actually calculate the structural parameters like lattice parameters, bond angles, bond lengths. So everything can be found using this X-ray diffraction. So further, we also use the scanning electron microscope. In principle, you must say the scanning electron microscope as a secondary electron microscope. Like for instance, in a scanning electron microscope, the electron gun will be there. So this electron gun will generate the electrons, and electrons will be impinged on top of the sample. Now, the thing is that from the sample, there will be many outputs. Like secondary electrons, backscattered electrons, augur electrons, X-rays, cathode luminescence light. So all these things will be byproducts as a result of impinging the electrons on top of the sample. It all depends upon what you would like to characterize from the material. For instance, if I want to know information about the morphology of the sample, you have to detect the secondary electrons. You put a secondary electron detector at appropriate angle, you can detect the secondary electrons. You can also detect the backscattered electrons. These backscattered electrons actually gives the information about different phases that exist in your material. For instance, if you have AB and AB1 or AB2, you can crystal clearly see the contrast between different phases that exist in material if you analyze the backscattered electron imaging. Okay, so now you'll also have the augur electrons. The augur electrons will give information about the structure from the fine top layers. This augur spectroscopy can be used for the thin film based samples, and you would also get X-rays from the samples. So from the X-rays, you can actually know the composition of the material. Okay, so that's why it's called energy dispersive X-ray spectroscopy, EDAX. Like basically, if you want to characterize your material, you have to know the morphology of the material. The morphology of the material can be obtained from the secondary electrons. The phases that exist in your material can be obtained from the backscattered electrons, and the composition of the material you can obtain from the X-rays that we receive from the sample. Okay, these are the three important extracts that we can obtain from the sample as soon as we impinge the electrons on top of the sample. Okay, so from these extracts, you can actually analyze your materials in a better way. You can actually say whether your material is in single phase or multi-phase, or whether the composition that you want, whether you have achieved or not. Such kind of information you can obtain from these extracts. Okay, So we also used a technique called vibrating sample magnetometer, like to detect the magnetic moment of the sample. Like it works based upon the Faraday's induction law. So whenever there is a flux change, there will be induced EMF in the pickup coils. So this EMF is proportional to the magnetic moment of the samples. Okay. So using the vibrating sample magnetometer, we also try to analyze the magnetic properties of the holmium oxide. So this is a kind of the magnetic field versus magnetization graph that we have obtained for the H2O film, the holmium dope or holmium added titanium dioxide film. Like it actually shows paramagnetic behavior. Paramagnetic behavior. This is the surface morphology that we have obtained from the SEM. Like the surface actually resembles very smooth and then without any discontinuity. And the film thickness is about 6 micrometers. And these are the JV characteristics, the current density versus voltage that we have obtained for HTO device, holmium added titanium dioxide based device. So here we used AM 1.5 spectrum. Like as I mentioned, like we have to impinge a light on top of the solar cell. So this we have used AM 1.5 spectrum, AM 1.5 spectrum. So this is the voltage versus current density graph that we have obtained. Like by considering the cell voltage V as negative and generated J as positive from zero potential to VOC, the resultant JV can be expressed with this expression. J is equal to this much. Okay. So now we fitted these graphs with this equation and obtained the solar cell parameters. What are the parameters that we have obtained after fitting this graph with this? Like we have obtained the open circuit voltage, the short circuit current density, fill factor, then efficiency of the device, the resistance shunt resistance. These are the parameters that we have obtained after fitting these graphs with this equation. Like for instance, if I consider the efficiency of the device, in the parent device, in the titanium dioxide based device, the efficiency that we have obtained is about 5.22, and in HTO device we have obtained the efficiencies of the order of 5.90. Now the question is, why there is an improvement in the efficiency of the device after we add holmium to the device. So this we have repeated several times and we could see the similar trend, the increasing trend after adding holmium to the titanium dioxide based device. Okay. So the probable reason for the enhancement in the efficiency of H2O based device can be due to the spin orbit coupling, of the holmium oxide. Because of this fact, efficiency enhanced and enhanced intersystem crossing. As I just discussed, like the intersystem crossing, like basically when we have electrons in the ground state, these electrons can go to the excited state. Like electrons which are there in the excited state, singlet state, they will have very less lifetime. Like for instance, if electrons comes to the triplet state, they can spend more time. Because of the addition of the holmium oxide to our device, the efficiency is like the transition between the singlet excited state to the triplet excited state is unlocked, which leads to the enhancement in the efficiencies of the device. So as more excitons dissociated in T1 state, in the triplet state, more electrons are driven to external circuit through conduction band of titanium dioxide, which leads to enhanced short circuit current density. Like as you can see here, the short circuit current density also enhanced when we add the holmium to the device. So like the one characterization that we have performed is JV characteristics. Like in order to support our results, we also have done the impedance measurements. Like the Nyquist plot, we also have plotted the Nyquist plot. Like as you can see here, the radius of Z for HTO device decreases. Let us try to understand why the radius has been decreased. So suppose what is the implications? Like suppose if the radius decreases, what are the implications? The significant decrease in the charge transport. Like if the radius significant decrease in the charge transport resistance for H2O device from 4.96 to 1.063 ohm centimeter square. So if the radius decreases means the impedance decreases. If the impedance decreases means like the resistance for the electron flow decreases. Okay, if the resistance for the electron flow decreases, that means more and more number of electrons flow through the device so that the efficiency of the device enhances. Okay, so this you can also understand by decreasing the resistance of H2O device from 4.96 to 1.063. Like initially the device resistance, the device resistance was at 4.96 for parent titanium dioxide, and as soon as we add holmium to the device resistance decreased to 1.063. Okay, from this we can say that from the impedance spectrum, from the impedance analysis, we can say that the resistance of the device or the impedance of the device decreased as soon as we added holmium to titanium dioxide based solar cells. So these graphs, these arcs, we fitted with this circuit and extracted the resistance of the device. So we also tried to plot it, the Bode phase plot and the Bode frequency plot. So Bode frequency, the impedance and the phase angle decreases with frequency. From these two graphs, what we can say that the impedance decreases, like this red colored graph. It is actually for titanium dioxide. The blue colored graph, it is actually for H2O device, holmium added titanium dioxide. The impedance decreases as soon as we added holmium to the device, and also the phase angle also decreases. Okay, the real part dominates and capacitive part diminishes. So like the real part dominates. The real part is huge, and then the capacitive part diminishes. So what is mean by diminishing of the capacitive part? Like for instance, if we say the capacitance of the device is more, what does it mean? It means that more amount of charge will be accumulated at one place without flowing. Like if the capacitive part decreases, that means the flow of current is more. Without accumulation of the charges. Okay, the less capacitive effects and the charge accumulation at the interfaces. If you have the more capacitance for the device, that means the charge accumulation will be more. If you have less capacitance, the flow of the electrons will be more. Like since the imaginary part decreases, what we can say is that the capacitance part or the imaginary part decreases, capacitive part decreases. As a result, the more charge flow within the device. We also try to analyze with the optical absorption spectra, like as soon as we added the holmium, the absorption of the device enhanced, because of the holmium is having high optical properties. Okay, we also tried to obtain the lambda versus alpha absorption coefficient, like alpha is equal to 4 pi k by lambda, and we try to analyze using the ellipsometry experiments. Like k is the extinction coefficient of the material obtained from the ellipsometry. What we could see is that the absorption coefficient of holmium added titanium dioxide is more in comparison with the parent titanium dioxide. So we also try to perform the photoluminescence experiments. Like here we excited at 527 nanometers, and we detected the emission at 728.5 nanometers. What we could see is that this blue color, for the H2O device, the photoluminescence quench. There is a quenching of the photoluminescence for the H2O based device in comparison with the titanium dioxide. What we can understand from this? What we can understand is that the quenching of the luminescent intensity for the H2O device is a clear evidence of increase in the intersystem crossing rate and excitonic dissociation rate. Like as we added holmium to the titanium dioxide, the photoluminescence decreases. What does it mean? It means if the photoluminescence is more, that means the more number of electron hole pairs will recombine. Since the photoluminescence decreases, that means the less number of electrons and holes are recombining. That means the more charge transport within the device. Okay, the reason why we have performed all these experiments is to support IV characteristics of our device. Okay, like we have performed JV characteristics from the solar cell device, and we have performed the impedance spectroscopy to support our results. And then we also have done the absorption spectra to support our IV characteristics, and ellipsometry absorption measurements, and also the photoluminescence measurements. All these experiments supported our results in the sense that as soon as we added holmium to the device, due to the strong spin orbit coupling, the efficiency of the device has been enhanced. So on top of that, we also tried to apply external magnetic field to the device with a single pole magnet. This is a single pole magnet which actually generates magnetic field in this form. Like for instance, if I have a two-pole magnet, the magnetic field would start from the north pole to the south. It will end at south pole. But however, in a single pole magnet, so this is how one can imagine the flux lines from the single pole. Okay. So now, why we have applied the external magnetic field? As I mentioned previously, there are various ways by which you can improve the efficiencies. One, by absorbing the more light from the sunlight, so that we could able to achieve using the dye. As the dye is having the broad spectrum, it can absorb more and more light. That is the first thing. The second thing is by spin orbit coupling. Like we have already seen that because of the spin orbit coupling, the transition between the singlet excited state to triplet excited state is unlocked. As a result of this fact, the recombination rate has been enhanced. We further would like to enhance the recombination rate by applying a magnetic field externally to the device. So you can ask me a question, how the magnetic field would enhance the recombination rate. Like for instance, if I consider electron which is moving within the device, if you apply electric field, the motion, the force will be along the direction of applied electric field. Now, if you apply magnetic field perpendicular to the electric field, so it would obtain a spiral motion. So what does it mean? Before it goes from positive to negative, positive electrode to the negative electrode, it actually would have a spiral motion. That means the electron is spending more time within the device before it recombines. Okay. So our main idea of doing all these things is to enhance the recombination time. If the electrons spends more time within the device before they recombine, the efficiencies of the device can be enhanced. One, we could able to achieve by transferring the electrons from the singlet state to the triplet state, as the triplet state would have the more lifetimes. Okay. The second one is through Lorentz force. This kind of phenomena is called as the Lorentz force, like application of both electric and magnetic fields perpendicular to the device. The electron would attain the spiral motion, which we can call as the Lorentz force effect. Due to this Lorentz force effect, electron would spend more time within the device before it recombines. As a result of this fact, the efficiencies of the device can be enhanced. Okay, this is the chart of the JV characteristics that we have obtained before we apply magnetic field and after we apply magnetic field. For instance, if I consider titanium dioxide, it is having the efficiencies of 5.22 in the parent compound, and then for H2O device, it is 5.90, and for H2O with magnetic field, it is 6.06. We have repeated these experiments several times. We could able to get the similar trend. So however, when we apply larger magnetic fields, what we could see is there is a decrease in the efficiencies of the device. It means that the fewer magnetic field, the very less amount of magnetic field would be beneficial to enhance the efficiencies, to increase the Lorentz force. So the efficiencies has been enhanced. Okay. Even if you can see the short circuit resistance, the short resistance, like it's increased and then further decreased. Okay. So the increase in the efficiency can be attributed to the Lorentz force, which leads to the enhanced recombination time. Okay. So the conclusions of this part, like we have successfully demonstrated the effect of heavy rare earth oxide modified photoanode to improve the performance of dye-sensitive solar cell based upon titanium dioxide. The powerful paramagnet, the holmium oxide, could produce a 13% enhancement in the power conversion efficiency of dye-sensitive solar cell. And this increase in the photo conversion efficiency is attributed to increase in intersystem crossing from the short-lived singlet exciton to long-lived triplet excitons. The photoluminescence measurements indeed infer a decrease in the emission intensity with the holmium addition. The improved charge transport within the device was affirmed by a low transport resistance as observed in the EAS, like impedance spectroscopy measurements. The finally application of external magnetic field as low as 100 Oersteds enhanced the device efficiency to about 6.06% due to an increase in the recombination time as a result of the Lorentz force that is experienced by the charges. We believe that our work would indeed play a major role in developing dye-sensitive solar cells based upon the magnetic phenomena. Like very few groups in the world are doing the effect of magnetic field on the solar cells. Of course, like there are nowadays even the sunlight is being changed to the electricity using the dielectric materials as well. Like it is a new direction to this solar cell field. Like one way is using the magnetic field, another way is using the dielectric materials. Already we have first generation solar cells and the second generation solar cells. So the new advancements, advancements will lead to new phenomena, and which will help the technology in a great detail. Okay. How much time I have still?
Sir, you can continue, sir.
I can continue, isn't it? Okay. So the another thing that I would like to emphasize is the effect of internal magnetic field. Like until now, we have used the spin orbit coupling and the external magnetic field. Like always, it is very difficult to carry an electromagnet along with the device. Okay. So now that spurred an idea in our mind that without using external magnetic field, if you use internal magnetic field, like how would it be? Like that created a new idea in our mind that if you use internal magnetic fields of the nanoparticles, that may enhance the solar cell efficiency. That is the origin of this work. The effect of internal magnetic field or demagnetization fields on the transport properties in FETO dye-sensitive solar cells. Okay, so this is the kind of device that we have developed. For instance, if you see, in addition to the titanium dioxide and dye, we also try to add the magnetic nanoparticles, which will have the stray fields around the nanoparticle. For instance, if you consider any magnet, any permanent magnet, what will happen? From the north pole to south pole, there will be flux lines. Okay, so whatever rings that I have shown around the nanoparticle, they are basically going from the north pole to south pole. Individual nanoparticle will act like a individual magnet that leads to flux lines from north pole to south pole. Okay, so using these flux lines, we try to improve the efficiencies of the solar cell using the internal magnetic field. Like earlier, we had to apply magnetic field externally using electromagnet. Now we removed the external magnetic field. We don't use external magnetic field at all. Instead, we try to add nanoparticle to the device, and so that this kind of information we can obtain directly. Like we can enhance the efficiency of the device using the internal magnetic fields itself. So this is the kind of the structure that we have obtained for Fe3O4. So the spinal structure with a tetragonal or 3-bar M space group, like it consists of the spinal structure, and we could see a ferrimagnetic behavior. The ferrimagnetic behavior for titanium dioxide plus Fe3O4 device. Okay, as you can see, this is a kind of ferrimagnetic behavior, and it is having the coercivity of the order of 501 isotopes. So these are the TEM studies, the transmission electron microscope studies. Like we wanted to prove that our device or our material is in the crystalline phase, and you can see that in the titanium dioxide, in the titanium in the TEM micrograph, we have the spherical and hexagonal nanoparticles are present. Like you can see, the shape of the nanoparticles are spherical, and they also have the hexagonal structure. The lattice spacing corresponds to 100 direction of anodized TiO2 and Fe3O4 nanoparticles. Like for instance, if we see the diffraction side patterns, like if we see, if you expand in this region, you can see the lattice planes, from the TEM, we have crystal clear lattice planes. From this, we try to calculate the gap between the lattice planes. It is very powerful technique to determine the structure of the material, to determine the particle size of the material, nanoparticle. So from the particle, we have calculated the particle size. We also tried to calculate the gap between the planes. The gap between the planes is found to be around 0.36 nanometers. Okay. The HRTEM indicates the lattice spacing corresponds to 100 direction of the anodized TiO2, and the SIAD pattern corresponds to the polycrystalline nature. Like you can see the diffraction rings. In the diffraction rings, we could see different rings. Had it been a single crystal, we should get only one ring. But however, since this is a polycrystalline material, we could see different diffraction rings in the SIAD pattern. Okay. So the summary of this slide is basically, using TEM studies, we have characterized our material. Like in the sense that the nanoparticles are having the spherical and hexagonal shape, and from the lattice spacing, we could able to find the gap between two lattices. Like it is around 0.36 nanometers, and also the diffraction ring confirms that our film is polycrystalline in nature. Okay, this is the kind of JV characteristics that we have obtained. Like as you could see here, the efficiency of the device, it actually changed from 2.52 to 3.72. In the earlier device, we could able to get the efficiencies of the order of 5, and after adding holmium, we could able to see the enhancement in the device. Over here, the initial efficiency of the device that we have obtained is 2.52, and after adding Fe3O4, the efficiency is found to be 3.72. The enhancement of 48% in comparison with the parent compound can correlate to the stray field generated by Fe3O4 nanoparticles. So essentially, due to the stray fields that exist with the nanoparticle, enhance the efficiencies of Fe-TO based devices. And again, we have done the electrochemical impedance spectrum, and what we could see is that for Fe-TO, the phase angle decreases and then the impedance decreases. And we also tried to measure the nanosecond phosphorescence measurements. They're actually like the quenching of the phosphorescence is evident for Fe3O4 added dye-science stage solar cells due to larger short circuit current. Like if you see the short circuit current, it is having larger, like for the Fe3O4 added titanium dioxide. So because of this, the phosphorescence counts decreased. What is meant by photoluminescence and the phosphorescence? It is actually like if the phosphorescence decreases, what does it mean? the recombination time enhances. Recombination time enhances. The similar trend has been observed in the phosphorescence data. The quenching in the phosphorescence is evident for Fe3O4 added dye-sensitive solar cells due to larger short circuit current density. And as the short circuit current density is large, the recombination rate is low, and the phosphorescence intensity must diminishes. Recombination rate is low, and as a result, the counts has been decreased in the phosphorescence data. Now, as we use the nanoparticles within our device, we also wanted to prove that there exist nanoparticles within our device. Like now, the question is how to prove that there exist nanoparticles in our device. Okay, so one technique by which you can prove that there exists a magnetic phase or magnetic material within the device is by magnetic force microscopy. Magnetic force microscopy. So what is meant by magnetic force microscopy? It is similar to atomic force microscopy. So the atomic force microscopy, in an atomic force microscopy, you will have a tip. A laser will fall on top of the tip. What you do is that you will slowly try to approach the sample. The tip will try to approach the sample due to the forces that exist, due to the van der Waals forces or any forces, the atomic forces that exist in the that exist between the tip and the sample. If it is atomic force microscopy, so there will be reflection or there will be repulsion. There will be repulsion due to this fact. The tip will move back and forth. Okay, so as we impinge laser light at the edge of the tip, so there will be deflection for this laser spot. Okay, so from this deflection, and we use a photo detector, PSD, position sensitive detector or photo detector, and which will detect the position of the laser spot. Okay, from the position of the laser spot, we can actually image the surface, whether the surface is smooth or whether the surface is rough or whether the surface is discontinuous. Such kind of information you can get from the atomic force microscope. For instance, if you consider a magnetic force microscope, instead of having a non-magnetic tip, you will have a magnetic tip. And when you try to image a magnetic material, as we know that a magnetic material will have domains and domain walls. Wherever domain ends, your stray field start, and again it will start at another domain. Okay, this kind of magnetic flux lines you can find on the magnetic material. When you try to bring a magnetic tip towards a ferromagnetic material, the force lines that will be emanated from the tip will interact with the force lines that exist on the ferromagnetic material. So there will be interaction between the flux lines of the tip and the flux lines of ferromagnetic material, which will give the magnetic interaction. This leads to this will give the magnetic phase. What kind of phase that exists. From the phase analysis, you can actually say whether the magnetic moment is oriented in the up direction or in the down direction. Look at based upon the color contrast. Like suppose if the magnetic moment is up, you can observe the bright contrast. If it is down, you can observe the dull contrast. Okay, so let's try to see like what kind of images that we have obtained. Like for instance, if you consider this is the topography image that we have obtained from the magnetic force microscopy, and this is H is equal to 0. That means initially we don't apply any magnetic field to the film. As a result of this fact, somehow we don't see any magnetic phase image. Okay, now to observe the magnetic phase, what we have done is initially we have applied 300 oysters, positive 300 oysters. What we could see is a bright contrast, and when we try to reverse the magnetic field to minus 300 oysters, so the same bright contrast has been transformed to the dark contrast. What does it mean? It means when we try to apply the magnetic field of 300 oysters, all the magnetic moments within the nanoparticle saturated in one direction which leads to the bright contrast. And when we try to apply negative 300 I states, the magnetic moments are oriented in the opposite direction. This leads to bright contrast. Okay. From this, we can say that the nanoparticles exist in the device. These nanoparticles are generating demagnetization fields. These demagnetization fields are improving the efficiencies of the solar cell device. Okay. So on top of that, we have proved that there exists a magnetic nanoparticle in our device, and then this demagnetization, the demagnetization fields due to the stray fields due to nanoparticles improved the efficiencies of the solar cells. Okay. We also have done some simulations. The simulations, deeper understanding about kind of demagnetization fields and effect of them on the propagation of the light. Now we also try to do the simulations to understand the demagnetization effects on the charge carriers. What we must know is that the minimum energy spin configuration and exchange field, how the exchange field is distributed within the device, and the demagnetization fields due to the magnetic nanoparticles. Okay. We also try to see the effect of demagnetization fields on the propagation of S and P polarization vectors. Okay. So the distribution of electric field components in general, for instance, if we say S polarization, it consists of electric field component in the X direction will be 0. The EY component will be EF plus EB, and EZ component will be 0. For a P polarization, EX is equal to EF minus EB into cos theta. EY component will be 0, and EZ is equal to minus EF minus EB into sin theta. If we say S polarization, the electric field components must be like this, and for a P polarization, the electric field components will be like this. In the presence of demagnetization fields, so the EF is the amplitude of incident electric field, EB is the amplitude of the reflected electric field, theta is the angle of refraction in the medium. Okay. So what we have done is we have done two different simulations, micromagnetic simulations. In addition to the experimental results that we have obtained, we also wanted to prove the kind of effect that we have obtained using the simulations or theoretical models like micromagnetic simulations. These micromagnetic simulations basically work on the Landau-Lipschitz and Gilbert equation. This is the equation that is given. The first term on the right hand side shows the gyromagnetic behavior of the system and the angular momentum associated with the interaction between the magnetization vector and H effective field. The second term actually gives the dissipation of the energy. What does it mean? This Landau-Lipschitz Gilbert equation is the one which gives the precessional motion of the electron. For instance, if I consider an electron, the electron will move around its equilibrium position, like around its own axis. That means the first part of this equation minus gamma naught m cross H effective, it actually shows how well the electron is spinning around its own magnetic field axis. The second part gives like how this precessional motion will be dissipated, how the spin motion will come to its original position with time. So these two parts will give, the first part will give the gyroscopic behavior, the second part will give the dissipation of the energy. So a finite difference method and using the mesh size as small as 0.25 nanometers has been used for our purpose. And over here the E total, the energy that we have used is the exchange energy, demagnetization energy, and the anisotropic energy. This is the kind of micromagnetic simulations that we have obtained. Like initially the magnetic moments, they are random, and we try to relax the magnetic moments, and this is basically the relaxed spin configuration after the energy minimization along the EZ axis in 100 direction. And this is the kind of exchange field that we have obtained. And the demagnetization field, this is the graph for the demagnetization field. What you could see is that the exchange interaction or the exchange field is restricted to the boundary of the nanoparticle, whereas the demagnetization fields they are extended out of the boundary of out of the boundary of the nanoparticle. So this demagnetization field actually helped in enhancing the efficiency of our solar cell device. Okay, so when the light is incident on the okay, this is fine. So now on top of the micromagnetic simulations, we also have done the transverse matrix modeling. So actually, this transverse matrix modeling gave the information about the absorbed energy density versus depth. Like as you go deeper into the depth of the solar cell device, how the energy is absorbed for a S polarization light from or the P polarization light. Like for instance, if we see a sunlight, it will have the S polarization. It can also have the P polarization. Okay. So now, like what will happen as the like as you go deep into the depth of light, depth of the solar cell, how the energy is absorbed, how this is the absorbed energy density for P polarization, and the blue curve represents for titanium dioxide, and red curve represents for FeTO. As you could see here, for FeTO device, the absorbed energy density is more at lower depths. I'm not finding any contacts to open. Sorry. The absorbed energy density is more for FeTO based devices. For instance, if you consider S polarization, the absorbed energy density is more for S polarization. That means as we added iron oxide nanoparticles to titanium based device, both the P polarization, the absorption capacity of the light has been enhanced within the device. So we also tried to calculate the Ex and Ey components with the depth. What we could see is that for iron added devices, the electric field component, the Ex and Ez component of incident light as a function of depth inside the device for P polarized light, and Ey component for the incident light as a function of depth inside the device for S polarized light, it actually decreases. The more amount of light is absorbed by the device for the S polarization and the P polarization. Okay. So the conclusion is that in the diffusive transport regime, like whatever IV characteristics that we have done, it's basically in the diffusive regime, because more and more collisions will happen. The diffusive transport regime, we could observe the efficiency enhancement in the dye-sensitive solar cells by incorporating the holmium oxide and iron 3 O4 nanoparticles. The holmium oxide nanoparticles have enhanced the solar cell efficiency by unlocking the intersystem crossing, and Fe3O4 nanoparticles have enhanced the efficiencies by the demagnetization fields within the device. So these demagnetization fields we try to prove by different methods like magnetic force microscopy, phosphorescence experiments, and we have done the micromagnetic simulations, and then also the transverse matrix modeling. And such kind of enhancement is supported through both the Lorentz force and improved intersystem crossing in the device as far as the holmium oxide is concerned. Whereas for iron oxide, it is due to the demagnetization fields, which leads to the Lorentz force effect that will enhance the efficiency of the solar cells. So the further understanding of the physics behind magnetic field effect on both the transport regime, actually like we have done using the transverse matrix modeling. Okay. Actually, like this is a complete work we have done. We have started from the scratch. We tried to develop the device. We developed the material. We characterized the material in a better way, and we tried to develop the device. We tried to characterize whatever results that we have obtained. We tried to characterize, or we tried to support with various sophisticated experimental techniques. We didn't stop at that point. We tried to use theoretical models or simulations to support our results, like micromagnetic simulations and transverse matrix modeling. Okay, this actually gives us a lot of happy that we have done a complete work in the sense that what is the effect of the magnetic fields or the magnetic phenomena on the efficiencies of the solar cells. We believe that this kind of complete work will help for the future technologies based upon the magnetic phenomena in solar cell devices. Okay, with this, I would like to thank everyone for your kind attention. If you have any questions, feel free to ask me.
Sir, for your wonderful presentations from the solar cells, constructions and working, different generations of solar cell. And the first generation, it was silicon. The second one was junctions. The third one was dye-sensitized solar cells. And then you said about factors affecting solar cells and the importance of dye-sensitized solar cells, which are eco-friendly and low cost. And different types of desensitized solar cells, which are N71 dye, titanium dioxide, and volume, and fabrications of different solar cells. And schematic diagram of solar cells and increasing the efficiency by adding aluminum to titanium dioxide, which increases the efficiency, decreases the impedance, and thereby increasing the absorption coefficient, and photoluminescence also increases. And the effect of external magnetic field.
No, photoluminescence decreases.
And efficiency of the device can be increased. The effect of internal magnetic field or demagnetization of
so a lot of noise is coming, sir. Lot of noise is coming.
Okay. Sir, I'm not audible?
Like background sound is coming, some noise is coming.
Okay. So that I'm audible. Now is it okay, sir?
No, still that sound is coming.
Now, sir, it is okay? Now, sir, there is...
No, whenever you speak, that sound is coming.
Network issues is the reason. Thank you for your wonderful presentation. So I request now I request my colleague Durga madam to raise the questions posted by the participants in the chat box.
Okay, sure.
Thank you so much, sir. Yes, sir. Am I audible, sir?
Yeah, you are audible, yes.
Yeah. Yes, sir. Thank you so much for sharing your knowledge, sir. Really, and it is really fascinating, and we enjoyed your motivational talk also, and hope the same with all of our participants, sir. So there are some questions posted by our participants in the chat box. The first one is posted by Dr. Srinivas Bura. He says that he is asking that what are the important parameters to be considered in the prevention of electron hole pairs?
Okay, so the important parameters, like suppose if you want to increase the electron hole pair recombination time, the most importantly, they should not recombine. That is what we have addressed in this work. Like basically, we try to enhance the electron hole pair recombination time. So by increasing the intersystem crossing. In the intersystem crossing, we try to unlock the transition between the singlet excited state to the triplet excited state. As a result of this fact, the electron spends more time in the triplet excited state, where you will have the longer lifetimes. And as a result of this fact, the recombination time enhances. The second thing we addressed by applying external magnetic field and internal magnetic fields. Okay, by applying the external magnetic field and internal magnetic fields, you are essentially influence the motion of the charged particles within the device. So the electron would attain the spiral motion due to which the electron will spend more time within the device. As a result of this fact, the recombination times would also enhance. Okay, this is how like one can improve the recombination times.
Okay, sir. Thank you, sir. And the next post is from the Savitri madam. Very informative session, sir. Thank you very much. I would like to know how to fit Nyquist plots and also whether ferrites can exhibit ferroelectric nature.
Ferrites, of course, like some materials, like they would exhibit ferroelectric nature. That is for sure. There are many ferrites which would exhibit ferroelectric nature. And then like the fitting the Nyquist plot, fitting like if you see this graph, just 1 minute. There are various free softwares to fit the Nyquist plot. Like these kind of circuits you can take, like whichever gives the best fit for your curve, that will be the circuit. Okay, there are various softwares to fit the Nyquist plots on the online.
Okay, sir.
Okay, what you have to do is initially you have to assign some values to different resistance values or capacitance values, and you try to interpolate so that you can actually get the best fit. First of all, you have to take your Z1 versus Z2 graph, then try to select a circuit from the software, and then try to get the minimum error. Standard deviation must be as minimum as possible, so that you can get the best output from the graph.
Okay, sir. Thank you, sir. And the next question is from Mr. Bharadwaj. What is the influence of magnetic flux at different locations of solar film on efficiency?
At different locations. Okay, so suppose if you have a material, if the particle size is very large or if the particle size is very small, and if these nanoparticles are located at different places, what would happen is the flux lines that would emanate from the North Pole to South Pole will be different at different locations. But however, like if you have a nanoparticle which is having the uniform size, which are distributed at different locations, I don't think there will be any change due to this flux lines. But however, if there is any size change of the nanoparticles, the flux lines will be different, and as a result, it would also influence the charge transport of the device. It all depends upon what kind of material that you choose. It is advantageous if you have the uniform particle size, so that the magnetic field effect will be uniform everywhere within the device.
Okay, thank you, sir. And the next question is, do you have studies on effects of variation of HO percentage and efficiency?
We didn't study that one. Like we chose the fixed amount of holmium, because the reason is that if you increase the holmium, it is a it is a paramagnet, and also like you will not have the thin film also will not withhold if you increase the concentration of holmium. Like there will be cracks within the device. Okay, that is why we had to restrict the amount of holmium that we added to our device. Okay, I mean, we wanted to increase the holmium, but however, what we could see is that many cracks within the device, which would influence the device characteristics.
Okay, sir. And next question is, which principle to work the solar cell? Maybe the principle of
photovoltaic effect. Basically, like you like a semiconducting. You take a semiconducting material, and the band gap of this semiconducting material must be almost in comparison with the spectrum that we receive from the sunlight. And as soon as light falls on the PN junction diode of material, of the semiconducting material, what would happen is electron hole pairs will be generated. Okay, these electrons will flow within the device, which will give us the current.
Okay, thank you, sir. And the next one is, you showed efficiency is increased in titanium plus ferrite materials.
Yes,
Do you
please.
expect the same for titanium, hafnium, and ferrite materials also, sir?
Titanium, hafnium.
Yes, titanium, hafnium, and ferrite, all the three.
See,
Ca plus HO plus Fe3O4. Yeah.
Can you repeat what is the final formula that you mentioned?
Yeah. Do you expect the same for Ti?
For Fe3O4, maybe it may enhance. It may enhance, but we didn't try that one.
Okay, sir. Yeah.
It is basically the combination of the spin orbit coupling and demagnetization fields.
Yeah.
It's basically like it. The system will be more complicated. See, like so, like initially, as I mentioned, like the graduate cell or dye sensitized solar cell, initially it gave efficiency of 2%. But however, by changing the electrolyte or by changing the dye or by changing the active material, people could able to enhance the efficiencies greater than 10%. Okay, that is one way of enhancing the efficiencies of the solar cells. But however, as we know that the entire current that goes through the solar cell device is based upon the electrons. Okay, so our motivation of doing this work is basically to influence the charge motion within the device. Okay, so that is the reason why we had to introduce a magnetic nanoparticle. Okay, suppose if you just apply magnetic field on top of the titanium dioxide, the effect may be very small. But however, if you introduce a nanoparticle, what would happen is it will generate internal magnetic field. It will generate the internal magnetic field. This magnetic field would change the charge transport within the device. Okay, so this is a new direction in the field of solar cells, where the magnetic field indeed can be used to enhance the solar cell efficiency. As I mentioned, like nowadays, the new trend is to enhance the solar cells using the ferroelectric materials. The ferroelectric materials also give the efficiencies of the order of 20%. Okay, so this is one direction, the magnetic field effects. The another direction is by having the multi-junction solar cells. Our way is to improve the solar cell efficiency with the magnetic field. Someone else method is to increase the efficiencies using the ferroelectric materials. So of course, one can also combine all these methods, but still a lot of research needs to be carried out. Okay, as of now, we hope that we try to create a new path to improve the solar cell efficiency using the magnetic fields or the magnetic phenomena.
Okay, thank you so much, sir. And this is actually the question and this record from my side only.
Okay.
How do you include this magnetic nanoparticle to the device, sir, like a ferrite particle or a ferroelectric material, either through doping or by making a composite material?
See, like if you clearly observe my presentation, throughout the presentation, I was very skeptical in doping and adding. Okay, I have never used doping.
Yes, sir. Yeah.
There is a lot of difference between doping
yes,
and
sir.
adding.
That is why I'm asking, sir.
Okay.
I'm asking, yeah.
Okay,
Yeah.
doping
yeah.
actually takes your element to the interstitial sites, but we didn't do that one.
Yes.
We
yeah.
just added.
Okay.
We just added, and then basically we have taken the titanium dioxide paste, and then we added some percentage of holmium or iron oxide nanoparticles to the titanium dioxide paste.
Okay.
We didn't dope. Directly we added to the paste and then made the thin films out of it.
Thin films. Okay.
Yeah.
So that means like a composite, like a type
it's a
of
kind
mixture.
of composite kind
composite.
of. Yeah, composite kind
yeah,
of.
yeah. That's what I just wanted to.
Okay, okay, fine. Yeah.
Very, thank you, sir. And then the next question from the participants. What is the software used for micromagnetic simulation?
For micromagnetic simulation, there is a software called WOMP. OMMF, Object Oriented Micromagnetic Framework. It actually works based upon the Landau, Lifshitz and Gilbert equation using the finite difference method. Okay, so this WOMP software, it is available freely online. You can directly download WOMP software, install it, and then you can generate any kind of the magnetization loops. Okay, so like even if you are expert in the WOMP software, you can publish many papers. Because there are various papers by which people have been publishing using the WOMP software.
Okay, sir. Okay, sir. Thank you. And the last question, I suppose, what is the deposition technique you adopted for coating thin films?
The deposition technique that we have adopted is basically, since we had to deposit a composite material, we had to use the spin coating method or drop casting method.
Okay.
However, one can also use the pulse laser deposition technique. But if you want to use the pulse laser deposition technique, you will deposit a titanium dioxide film only, but you cannot add the holmium or ferrite nanoparticles to the titanium dioxide. That is why we used a spin coating method or drop casting method to develop our thin films.
Okay, sir. Yeah, I think. Yes.
Madam?
Yeah. This is the last question, I think, sir. Yeah.
Am I audible now?
Yes.
Yes, sir. Yes, sir. Yeah.
Okay, ma'am. Thank you, madam. Thank you, sir, for clarifying the doubts by answering all the questions raised by the participants. Thank you so much, sir. Now I request my colleague, Dr. I. Lakshmi Prasanna, madam, to propose the vote of thanks.
Thank you, sir. An ignited mind is the most powerful weapon on the earth, above the earth, and under the earth, and it's got through education. A very good afternoon to everyone present here. On behalf of Vignan Bharati Institute of Technology, I, Dr. Lakshmi Prasanna, take this as a great honor and a privilege to deliver the vote of thanks. First of all, I would like to thank Professor Suryanarayan Garu of IIT Hyderabad for delivering such a wonderful and inspiring lecture on magnetic field effect on titanium dioxide based dye-sensitized solar cells. Words are not sufficient to thank you, sir, for delivering such a lecture and spending your valuable time for us. No event can happen without the provision of vast network of people. So I would like to thank all the participants who gained the knowledge by attending this session. Last but not the least, I would like to thank the management of Vignan Bharati Institute of Technology and our principal, sir, Dr. G. Amarendra Rao Garu, and Vice Principal and HOD of H&S, Dr. Sridhar Garu, and the Director IQAC, Dr. Kulakarni Garu, and the Registrar, Dr. Satyanarayan Garu, and the Subject in Charge, Dr. K.V. Dharmendra Kumar, and my faculty members for giving me this opportunity to present the vote of thanks. Thank you, sir. Thank you once again for your valuable lecture.
Sure, madam. Thank you very much.
Thank you.
Yeah.
Madam, please post the feedback link, madam.
Sir.
Okay.
Sir. Okay, sir.
Okay. Thanks.
Thank you, sir. Thank you very much.
Thank you very much. Yeah. Thank you. Yeah.
And
One
thank
more to all the participants, sir. Due to some technical issues, we are not able to post the feedback form now. I'll post it within 1 hour in the WhatsApp group, sir.
Okay, ma'am. Thank you. So I thank all the participants for joining the webinar and making it a grand success. Thank you all. Thank you, sir.
Thank you.
Thank you. So I'm ending the meeting now.
Yeah.
Thank you.